Usually when we kick off a deep dive, I like to start with a rhetorical question, maybe a quirky historical anecdote to set the mood. But today, we just don't have time for that.
No, today is different.
We have to start with a red alert. And I don't mean that metaphorically. In February 2026, Google, specifically Kent Walker, their president of global affairs, and Hartmut Neven, who runs Google Quantum AI, they issued a public warning that, well, they basically said the sky is falling.
It was a real all-hands-on-deck moment. I mean, you don't often see the executive level and the deep tech research level come together to issue a joint statement like that.
Unless something massive is on the horizon.
Exactly.
And they didn't mince words. They said, quite plainly, the encryption currently used to keep your information confidential and secure could easily be broken by a large-scale quantum computer in coming years.
It's the kind of statement that should stop every CISO, every banking executive, and frankly, every person with a smartphone in their tracks. We're talking about the mathematical backbone of digital privacy. Everything. Banking, state secrets, your personal messages, just snapping like a twig.
And that sets the stage for today. We are looking at this terrifying problem, the imminent collapse of digital privacy. But, and here's where the story gets really wild, we're also looking at a solution. A fascinating, almost cinematic architecture that appeared just 2 months before Google sounded the alarm.
It really is a Noah's Ark situation. Google predicted the flood in February, but it turns out someone else had already started building the boat back in December.
So let's unpack that threat first, because I want to make sure we all understand the stakes. Google listed 5 specific dangers, but the one that kept coming up, the one that honestly sounds like a plot from a spy thriller, is store now, decrypt later.
SNDL. Yeah, it's the nightmare scenario.
But let me play devil's advocate for a second here. Storing data is expensive. We're talking about exabytes of encrypted traffic. Are bad actors, nation states, criminal groups, are they really investing that much cash just to harvest gibberish they can't even read?
Right. Is the payoff worth it?
Yeah, is it?
And the answer, absolutely yes, because data has a shelf life. Look, your grocery list from today won't matter in 2030. But what about long-term intelligence, diplomatic cables, layouts of power grids, genetic data, proprietary pharmaceutical research? That stuff is valuable for decades.
Okay.
So yes, adversaries are harvesting it now. They're storing it on these massive server farms, just waiting for a quantum computer powerful enough to shatter the RSA or ECC encryption that's protecting it.
So it's a waiting game. They grab the safe today, and they wait 5 years for someone to invent the blue torch that can cut it open.
Precisely. And Google's warning highlighted that this isn't, theoretical. It's happening now.
Yeah.
But there's another layer to the threat that I think is even more insidious, and that's the legacy problem.
Right. This was the part of the Google report that really stressed me out. Because in a perfect world, if encryption breaks, you just push a software update, right?
Yeah, like updating an app on your phone.
But Google pointed out that for critical infrastructure, it's not that simple.
Not at all. I mean, think about satellites in orbit or the embedded systems controlling a dam or even the mainframes at major banks.
Yeah.
A lot of that encryption is hard-coded right into the hardware.
You can't patch it.
You can't just patch a satellite that's floating in geostationary orbit.
Yeah.
To fix the encryption, you'd literally have to launch a mission to replace the physical chip.
Which is impossible. Okay, so we have fragmented systems, hard-coded vulnerabilities, a ticking clock. And this brings us to the frustration I felt reading the Google announcement. They described the problem perfectly. They shout, fire. But when it came to the solution, it felt a little, I don't know, policy heavy.
There's very consultant speak. Modernize to the cloud, form committees, adopt NIST standards. Basically, they told the world you need to change your locks immediately.
But they didn't exactly hand anyone a new vault. They pointed at the burning building and said, you should probably have a sprinkler system. But they didn't bring the water.
But someone else did.
Enter patent, #65. This is where we pivot from panic to what I can only describe as engineering arrogance in the best way possible. There's this entity called 7Q7 Labs, and in December 2025, 2 full months before Google's panic button, they filed a provisional patent for something called the Recursive 7 to the 4th power lattice cryptographic shell system.
It is a mouthful, but every single word in that name matters.
The timing is just. It's either suspicious or incredibly serendipitous, but let's look at the math. Recursive, 7 to the 4th power, that's the architecture. So 7 times 7 times 7 times 7.
Right, that gives us 2,401.
Now, for our listeners who follow crypto, we know standard encryption usually relies on one really, really hard math problem. But this system seems to be relying on just sheer volume Or complexity? What does that number 2,401 actually represent?
Think of it as a combinatorial explosion. So traditional encryption is like having a front door with one deadbolt. Google is saying quantum computers will snap that deadbolt. Patent hashtag 65 takes a completely different approach. Instead of one door, imagine a fortress with 4 concentric walls. To get to the center, you have to pass through 4 gates.
4 shells. Got it.
But here's the kicker. At each wall, there isn't just one gate. There are 7 distinct gates. And to send a message, the system picks 1 gate at the first wall, 1 at the second, and so on.
So the number of possible paths through that fortress is 7 times 7 times 7.
Times 7.
Which is 2,401. It's not just a stronger lock, it's a maze that changes.
Exactly. And the ingredients of those gates are what makes this so revolutionary. This isn't just about using more math, it's about using different math.
Okay, I want to drill down on that because reading the technical specs for Shell 1, the application layer, it felt like looking at a United Nations meeting of cryptography. You've got AES from the USA, Camellia from Japan, ARIA from Korea, SM4 from China.
This is what we call algorithmic diversity. And frankly, it's a stroke of genius.
But why does the geography matter? I mean, is math different in China than it is in the US?
The math isn't different, no. But the trust is. Look, in the crypto community, there's always this low-level paranoia that a national standard might have a backdoor. You know, maybe the NSA weakened AES just enough so they could read it. Maybe the Chinese government did the same thing with SM4.
So by mixing them?
Exactly. By layering them, you are using geopolitical distrust as a security feature. If you wrap a message in American AES, and then wrap that in Chinese SM4, and then wrap that in Korean ARIA, you're essentially betting that the NSA, the Chinese Ministry of State Security, and the South Korean intelligence agencies are not all secretly working together.
That is a fascinating way to look at it. If the NSA has a key to the first door, they still get stopped by the Chinese door.
Right. It forces an attacker to break multiple unrelated mathematical problems designed by different cultures with completely different biases. It's redundancy, like a RAID array for hard drives, but for secrecy itself.
So that's Shell 1. Then you have Shell 2 and 3 handling transport and network verification, making sure the message wasn't tampered with. But Shell 4 is the heavy artillery. This is the direct answer to that Google quantum warning.
Shell 4 is the outer layer. This shell contains 7 post-quantum primitives. These are the specific algorithms that NIST, the National Institute of Standards and Technology, has spent years testing to see if they can survive a quantum attack.
We're talking about Kyber, dilithium, CEFCS, plus the big one?
Yes. Kyber for key encapsulation, dilithium for digital signatures. These are the gold standards. But usually a company picks one. They say, okay, we're upgrading our whole system to Kyber.
Right.
Patent hashtag 65 says, why choose? It includes Kyber, dilithium, Symphony-NS, plus Maker, plus Magellan, Bike, HQC, and Frotocom. The whole shebang.
It's the kitchen sink approach.
It's a hedge. Google warned that one clever quantum algorithm could break a specific encryption method. By wrapping the data in all of the top contenders, you're insulating yourself against the unknown. Even if a mathematician discovers a flaw in Kyber 5 years from now, your data is still locked behind Magellan and Frotocom.
That is incredibly robust. But here's where I want to push back a bit. We've established it's a fortress with 2,401 paths. But if the keys to those paths just stay the same, eventually a supercomputer could map the whole thing, right? I mean, static defenses always fail.
You're absolutely right. Static defenses are sitting ducks. And that's why the most innovative part of patent hashtag 65 isn't the walls, it's the movement. It uses what's called a 60-cycle rotation.
Okay, walk us through the mechanics of that.
So the system is programmed to rotate the keys and the pathways every 60 cycles. Now the math here gets really, really elegant. We have 2,401 total pathways. The rotation cycle is 60.
And I noticed the patent makes a big deal about the fact that the greatest common divisor, the GCD of 60 and 2,401, is 1. Why does that specific detail matter so much?
It's called coprimality. It's everything. Think of 2 gears spinning. One has 60 teeth, the other has 2,401 teeth. Because they don't share any common factors, they don't sync up or repeat a pattern easily. Every time the small gear turns, it engages a totally different part of the big gear.
So it prevents a pattern from forming that a hacker could predict.
Exactly. It guarantees that every single one of those 2,401 pathways gets a unique key at every single epoch. If you do the multiplication, it creates over 144,000 unique key pathway combinations.
Wow. And this brings us right back to store now, decrypt later. So if I'm a hacker and I spend 10 years trying to steal a key and I finally get one.
You've just wasted 10 years of your life. Because of that rotation, the key you stole is only valid for 160th of the cycle. You might decrypt a tiny sliver of the file, maybe a few milliseconds of audio or one line of a document, but the system has already rotated to a new key and a new pathway for the next chunk of data.
It turns a catastrophic breach into a minor glitch. It bounds the exposure.
Yes, it completely destroys the ROI for the attacker. Why spend billions building a quantum computer to crack a code if the prize is just 160th of a file?
Okay, this sounds incredible in theory, but I can hear our skeptical listeners, and probably the CISOs out there, asking the practical question. Is this just a white paper? Is it vaporware?
That's the first thing I looked for, and the answer is no. It's working code. The documentation details a Python implementation that is, right now, running on a Mac Studio.
A Mac Studio, that's consumer hardware.
That's the point. It doesn't require a supercomputer or a specialized server farm. The overhead is low enough to run on a high-end desktop, which implies it could eventually be optimized for drones, for medical devices, maybe even smartphones.
And what about the quality of the encryption itself? I saw a stat about a compare endpoint test showing a 50.43% bit difference. For the non-cryptographers out there, why is 50% the magic number?
That refers to the avalanche effect. In cryptography, if I change one letter in a message, I want the encrypted output to change completely randomly. I don't want it to look 99% the same. A 50% bit difference is like mathematically perfect randomness. It means the two outputs are completely uncorrelated.
So if I send the exact same message through pathway A and then again through pathway B, the encrypted results look totally different.
Yes. They measure the difference between all the pathways. And that 50.43% result proves cryptographic independence. It means that if a hacker somehow cracks pathway A, they've learned absolutely nothing that helps them crack pathway B. They are starting from zero every single time.
Okay, so it works, it's efficient, it's mathematically sound. Let's talk market. Who actually buys this? Because post-quantum crypto is projected to be a $17 billion industry?
The obvious answer is defense, but there's a specific feature in patent #65 called Claim 24 about non-overlapping subsets that is a total game changer for the military.
Right, I saw this in the notes, non-overlapping subsets. How does that apply to, say, the Army and the Navy?
Okay, remember, we have 2,401 pathways. You can mathematically carve that up. You can assign pathways 1 through 500 exclusively to the Army. Then you assign pathways 501 through 1,000 to the Navy. Because of that cryptographic independence we just talked about, even if the Army's system is totally compromised, spy in the base, keys stolen, everything, the Navy's communications remain 100% secure.
That's massive for compartmentalization. You can segregate data on the same network without needing a physical air gap.
Exactly. And it applies to healthcare, too. You can separate patient billing data from genetic research data. And speaking of healthcare, think about the timeline. If you're protecting a genome, you need that to be safe for 70, 80 years.
And Google explicitly mentioned AI in their warning, didn't they?
They did. Their second recommendation was that AI systems have to be built with post-quantum cryptography. If you're OpenAI or Google and you're training a model that costs $10 billion to compute, the weights of that model are your crown jewels. You do not want someone stealing them.
Right.
Patent #65 wraps that AI model in a four-shell defense, ensuring that even if someone gets into the server, they can't extract the model logic.
You know, we started this episode with the Google warning, the all-hands-on-deck alarm. And looking at patent #65, I keep coming back to that analogy you mentioned at the start.
The Noah's Ark analogy.
It's right there in the source material. Noah built the ark before the flood. Joseph stored grain before the famine. It feels a little dramatic, but given what Google is saying...
It's not dramatic at all. It's history repeating itself. Google, with all its massive resources and quantum expertise, just played the role of the meteorologist. They predicted the storm. They told us the flood is coming in 2028 or 2030. But this small lab, 7-7, they actually built the boat.
And they finished it 2 months before the weather report even came out.
Exactly. And that, for me, that's the real takeaway here. We always wait for the tech giants to save us. We assume Microsoft or Apple will just push an update that fixes the quantum threat. But in this case, a small, agile lab solved the biggest problem in computer science before the giants even finished describing it.
So, for the listener, whether you're a CISO, a developer, or just someone who doesn't want their digital life exposed, what does this actually mean?
It means the era of good enough encryption is over. You can't just have a lock on the door anymore. You need depth. You need agility. If you aren't looking at solutions like this layered, multi-algorithm rotating architectures, you are effectively standing naked in a snowstorm that hasn't started yet, but you know is coming.
Google's final quote in their warning was, "We need an all-hands-on-deck approach to make sure the quantum era is defined by breakthroughs, not breakdowns."
And I'd argue that patent hashtag 65 isn't just hands on a deck. It is the blueprint for the ship itself. It's the vessel that gets us from the classical era to the quantum era without sinking.
If encryption is the immune system of the internet, it sounds like we just found the vaccine.
I could not have put it better myself.
We're going to wrap it up there, but I want to leave you with a provocative thought. When you lock your door tonight, think about how many layers are standing between you and the outside world, and then think about your digital life. Do you have one lock, or do you have 2,401?
Something to keep you up at night.
Or, knowing this technology exists, maybe it helps you sleep a little better. Thanks for listening to The Deep Dive. We'll catch you on the next one.